Welcome everyone. In today's video we'll be solving a first order differential equation. So our problem is as follows. So we have x tan of y over x plus y, all in brackets, dx minus x dy equals 0. So when you look at this, you can probably tell right off the bat that you're not just going to be able to use the separation of variables as it is. So what we're going to have to do is we can introduce a new function. So what I'm going to say is let v of x equal to y over x. So v of x is a function of x. From here on out, I'm just going to write it as v. Okay? So v of x is equal to y over x. So what I can say therefore is that Vx is going to be equal to y. Okay, so that's going to be very important later on. And also what I can say there then is that dy dx, so this is going to be the derivative of Vx. Keep in mind that v is a function of x, that's why it's important to remember that here. And what we find is that dy dx is equal to v plus x dv dx. Excellent, okay. So what we've got now is we've got our initial problem and we've got a whole heap of different substitutions that we need to make. So first things first, I'm just going to go through and divide by d of x across our entire problem. So now we're left with x tan y over x plus y minus x dy on dx equals 0. Okay, fantastic. So at this stage here, what we can do is we can actually now make those substitutions. So anytime I see a y over x, I'm going to put a v in. Anytime I see a y, I'm going to put vx. And anytime I see dy dx, I'll put v plus x dv dx. Alright, let's see what our problem becomes now. So now it should read x tan of v plus xv minus x bracket times by v plus x dv dx, and that of course is still going to be equal to 0. Okay, fantastic. So let's go through and let's expand that and let's see what we have. So we'll go through and again we still remain with the x tan v plus xv, and now we'll subtract. Now it's going to be minus xv minus x squared dv dx equal to 0. Okay, so at this point here, what we recognize is that we have a plus xv and a negative xv. So what I can do is I can just go through and just get rid of those. And what I'm also going to do here is I'm just going to quickly move this term over to the right hand side, just so that way it's positive. And so what we'll be left with is x tan v equal to x squared dv on dx. Okay, so now is the point at which we can perform our separation of variables and then integrate as we normally would. Alright, so let's see what we are left with. So then it should be 1 over x dx is equal to 1 over tan v dv. Alright, so here we just need to integrate. Okay, so what we're left with is just going to be the natural log of x, and I might just put the constant term on this side for now, and I'll say that that is now going to be equal to the natural log of sine of v. Alright. Okay, so what I'm going to do now is I'm just going to take the exponential of both sides, and so what we'll have is that sine of v is equal to x, and instead of putting an exponential of c, I'm just going to put maybe c1. Alright, fantastic. So at this stage here, we're pretty much done. But what we do need to remember now is that v is equal to y over x. So making that substitution, what we're left with is sine of y over x equal to c1 x. And we could stop here, although this actually represents more of a dynamical system, so this won't necessarily be an exact solution to some sort of ODE. So what we can do is we can just take it a couple steps further, not worrying necessarily about the specifics for now, and take the inverse sine and then just simply multiply by x, and then we'll be left with y is equal to x sine inverse of c1 some constant times by x. And that's it. And I just wanted to really quickly go through what I was talking about earlier when I mentioned the dynamical systems. So if we have the last stage where we had y equals x sine inverse of x, then yeah, we get a lovely solution here. And it goes from -1 to 1, and from 0 to pi on 2. And that's fine. That's what we would expect when we look at a function like this, and there's no real stress there. However, when we take the other stage that we had, where we had sine of y of x equals x, what we have is we actually end up with this dynamical system with these chaotic orbits. So Desmos unfortunately doesn't have the graphical capabilities to go on forever, and as you can see, just after zooming in a little bit, it's said over here, this equation contains fine detail that has not been fully resolved. And that's fine, Desmos, you've done an excellent job so far, but what is quite nice to note is that it almost looks like a pair of scissors. And there we go. And so these orbits will continue forever and ever as we go up and up and up and up, or down and down and down. And there we are. So that is our dynamical system of sine of y over x equals x, and our actual solution of y equals x sine inverse of x.